We go to chapter 27. 27 is dealing with the light behave as a wave. So in which cases we like to say is called wave optics. Now chapter 26. If you go to major in physics, chapter 36 is a one semester class. That means one semester class in the third year physics. One semester, chapter 26. And then the chapter 27 is again one semester class in one semester class, means 15-week classes. In the junior level classes at UCLA, Okay, so we like to mention that to you. So if it behave as a wave, so this in this case is a light behave as a wave. So if it's a wave nature, so the light, if the light point in here, and it's spread out like an ocean wave. It's spread out like this, and it's not only go to one direction; it's go all the direction. So go propagate like this. So it's a wave function. It's a wave. So if it behaves as a wave, then the light has what? Has a speed v, and has a frequency f, and have a lambda. In which case, the lambda is called wavelength. So if we draw the light propagation, is usually is like this. It propagates like this. So a lot controversial about this light behave as a wave, light behave as a particle. A lot of people argue with this, and then there's a two side of theory or debate. One side is the person who suggests light behave as a wave have two persons. One is called Huygens, in which case it is from Germany. At the same time, another one is like that, is a famous Young. Young is from England. Young did a lot of stuff in physics. Young's modulus is his contribution. Young's modulus is his contribution. Then the wave theory is these two people strongly suggest this. However, they have a strong, one person is strongly opposed them. The gentleman is called Isaac Newton. Isaac Newton against the light behaves as a wave. So in those kind of things, it's called politics. So if you do something against Isaac Newton, basically you are not favorable son or favorable scholar. So they under a lot of attack by the other scholar because Isaac Newton do have a great influence. But thank goodness, this gentleman is called Huygens and Young. Basically, they try their best to the first guy, Huygens, develop the experiment, develop the theory, And the Youngs developed the experiment. Okay, when you're doing this experiment, you got to have a very pure light. Means the light only can have one wavelength. Back in those days, the thing have a one wavelength and one color turned out to be sodium light. And even sodium light, if you look at the spectrum, sodium light again has a very narrow double band wavelength. So when you're doing this experiment, for Young's experiment, using the what we call using the sodium light to do, basically set up that Young's experiment in the lab. Back in 1960, 66, 64, I did it. Takes almost a week to set it up. A week, try to tune it, and then finally see the phase image, phase phenomenon. That phenomenon is called interference fringes. That takes a week, right? So nowadays, if you ask me to do this experiment, I can do in 1 microsecond. Why? I'm using laser beam. And go through the double slit and go through this experiment. So now let's go through the theory section, in which case is on 27.3. 27.3 is called interference. Interference. Now all this interference, the good thing about this interference have a great impact in our daily life. You carry the result of interference. What's that? Your credit card, your driver's license. That is the result of this interference experiment. So Hodgkin said, suppose there's one light source, and then you go through a thing called double slit. Double slit. So you draw this. So they have a double slit in here. So in here. So suppose you have a light source. Light source here. Why you go to a double slit? Because you want to have a fine opening. When this opening getting smaller and smaller, then it will have the wave effect, wavefront effect. When the opening, when it becomes big, the light just goes through, walk through, cannot see the light behaves as a wave phenomenon. When it's getting smaller and smaller, then you have wave phenomenon. So we predict the wave propagate. So when you have a wave propagating up to this, what we call the double slit, in which case it's S1 and S2. So the opening is here. Okay, this is the screen you're watching. Now, ladies and gentlemen, there's one very important fact in here. If the light travel is blocking right at the center, according to Isaac Newton, the light is blocking here, so there's no light will be transmitting to this side. So according to here, according to light behave as a particle, light behave as a particle. No light at this point, we call center point. No light at the center point. As center. Because it's a blocking by this. Blocking by this. So now, say it simply, the light is in here, become a new light source. It's propagating. So it's propagating in here. It reach to here. So the light travel and then reach out here. and the light come out here, and then it will do the same thing. Will reach the out there. Out there. Okay, so we created another terminology. That means when the light travel like this, is a sine wave. If the sine wave travel in here up to here, they are in phase. In phase. It means in phase means in the same phase front. Same phase front. Or the same wavefront. So if they are in phase, in the same wavefront, what does it mean? Means this S1 light is propagating up and down like this. What's S2? S2 is propagate up and down in the same way. This is called in phase. Okay, then what is our phase? Our phase is like this. One light source is go like this. Another light source go up like this. This is the hour phase. So if this light come across one another, this will be cancelled out. But if this light have the same phase, this will be adding together. In which case, this case is S1 and S2 called constructive interference. And in here, we call destructive interference. Destructive interference. Okay, so in the reality, this constructive interference give you the bright spot. Or if it's a slit, it can become a bright rectangular. And this one, because of destructive interference, it cancel one another, will give us a dark spot. Dark spot. So according to Huygens, because this light, if it's the right ascender, if this light travel from here to here, is that means S1C equal to S2C. So consequently, they are in phase. So their prediction, according to here, because this is in phase, so Huygens predict under this condition we'll have a bright spot, bright strip or spot. That's what he defined. So now you're looking at it, it's very simple, obvious. But in those days, around 1680 or 1670, it's very difficult. It's very difficult to get that. It's next to impossible for somebody to understand this. The gentleman is a French, Huygens, I think it's German. And then England, the Young is very close by with Isaac Newton. He quietly do this experiment. And for those days, doing this experiment, it is extremely difficult, but he making it. So anybody should get Nobel Prize, he is the one, okay? He put up a lot of effort to do this one. And after this is discovered, prove that light behaves as a wave, then the whole area about optics is explosion, doing a lot of study on this kind of stuff. So we like to go through the somewhat the